Yes, okay. So for the second talk of the session, we'll have Nicolas Brunner from the University of Geneva, and he will talk about genuine network quantum non-locality. So Nicolas, the floor is yours. It is an online talk.
All right, so can you hear me well?
Yes, yes, yes.
Okay. Well, thanks, Marc-Olivier. Thank you to the organizers. Apologies for not being present with you in Zurich. I have a pretty bad cold, and when my alarm rang at 6 a.m. in the morning, I didn't feel the strength to jump in the train. But okay, hopefully I can still entertain you here from my room in Geneva. Okay, so the talk of today is on genuine network quantum non-locality. So network non-locality is a question that kept some of us busy for the last couple of years. And one of the sort of key questions there, at least in my opinion, was whether the network structure allows for novel forms of quantum non-locality. And so this is a question that well, kept us thinking for a long time. And here in this talk, I'd like to present a first proposal for such a notion. And so I'll try to convince you that this notion leads to something interesting. All right. Okay, so this is joint work with many different people. So the notion in itself that I'd like to present is joint work with Ivan Supic, who is now working in Paris, Tsai Yu, who left research and is back in Singapore, and Jean-Daniel Bancal, who also moved to Paris. And I also present some more recent results with people in Geneva, so Pavel Sikacki, Antoine Girardin, Sadra Boreiri, and Patrick Lipka-Bartosik. All right, so our starting point is the good old non-locality of John Bell, which you can see in this picture on a typical Sunday, probably in his office, thinking about Bell experiments and quantum optics and so on. And so I guess, as you all know, the point in Bell non-locality is to consider a setup with Alice Bob sharing some physical resource and performing some local measurements. So we typically have these input choices for Alice and Bob, right? And these give rise to outputs. And then we look at the statistics and we say lots of things from there. All right, so now going to networks leads us to the following situation where essentially we depart from having our simple Alice and Bob non-locality Bell test. In the following way, now we have many more nodes or parties. And you see these nodes, well, they share physical resources distributed by these sources here. And the key assumption that we would like to use here is that these sources are independent. And so this sounds a priori like a very reasonable model, and okay, doesn't look too complicated at first sight, but it's actually a very deep idea that was proposed more than 10 years ago by Cyril Branciard, Stefano Pirogno, and Nicolas Brunner. And so, well, there are many hopes by looking at non-locality now in this new setting of networks. To my view, one of the biggest things here is really to look for new forms of quantum non-locality. And of course, why do we expect this to be possible? Well, it's because in this network structure, we go beyond the resources that are typically used in Bell non-locality. So in Bell non-locality, we would have this source here, for instance, connecting Alice and Bob. And so, of course, we may have some entanglement generated by this source here. And then the parties may perform incompatible measurements. But what we do not have access to typically in Bell non-locality is somehow the other facet of entanglement, namely that of measurements, right? So you can think of the famous Bell state measurement that is used in teleportation and so on. And here the intuition is that whenever you will combine the entanglement of states with that of measurements, you may get really much stronger forms of correlations. So that sounds quite reasonable as a first intuition. However, demonstrating and formalizing this problem turns out to be quite challenging. All right, so why is it so difficult and so different from the standard study of Bell non-locality? Of course, Bell non-locality has also been discussed for scenarios where you have many observables, like drawn here. But here you see the main idea is that they are all connected by one source, right? And so this has the property to make the problem relatively simple, I would say, because all sets of relevant correlations become convex. And then we can go ahead with our good old linear Bell inequalities. And then we have polytopes and things like this. So there, I'm not saying that we understand everything, but we have a pretty good general understanding of the situation. And we have methods that work pretty effectively in practice. Now, when you move from here to there, well, all of a sudden, all this beautiful framework breaks down and becomes essentially useless. And really the reason is this independence condition between the sources, which makes the problem non-convex, and then we need nonlinear type Bell inequalities. And really we essentially lack appropriate methods to describe properly the physics here. All right, so let me give you an example of interesting network non-locality. So here is our favorite network, the triangle. So it has these three parties connected by each pair of party being connected by a bipartite source. And you see each party providing some output result, right? Which is based on making some measurement here on these incoming two particles. Maybe something I didn't emphasize before. So what is new here and why it's interesting and relevant to discuss about entangled measurements? Because you see this party here has two subsystems that arise from independent sources, and therefore there is a natural notion of bipartition. So here it makes sense to talk about an entangled measurement, while in standard Bell non-locality it usually doesn't. All right, so this is our network here, and you see there is already one striking difference here with the standard setup of Bell non-locality is that we have no inputs, right? So each party makes a fixed measurement. There are no input choices. Yet, well, okay, so there are interesting things to be said here. First, let me take you to some definition. So what does it mean to be classical in such a network? This is a notion that we typically refer to as being tri-local, because you have these three independent sources. And so I would say here, the idea is really very similar and inspired from Bell non-locality, in the sense that you have these sources here that produce classical variables, and so therefore you will be looking at decomposing observed data probabilities in the following form. So there is first some distribution for each of these variables here, and you see the main thing is that this distribution will factorize. Okay, that's our key assumption about the triangle. And then each party here, for example, Alice, has a local response function that will generate some output A, given the incoming variables gamma and beta, right? And it's the same for B and C. Now, well, strikingly, I would say, it's actually possible to demonstrate non-locality in this network, even though there are no inputs. So this is quite astonishing when you come from Bell non-locality, because there the fact that observers can locally choose their settings is absolutely fundamental. But if you move to this architecture, you no longer need it. So this is an effect known as quantum non-locality without inputs. And so the first very elegant demonstration of this effect was proposed by Tobias Fritz already 10 years ago. And this is a very clever idea whereby you would like to embed a standard Bell test, for example, testing the famous CHSH Bell inequality. You want to embed this in the triangle network. So how do you do it? Well, in a Bell test, Alice and Bob, so Alice and Bob will be our key parties doing the Bell test. They should share some entangled state. This is a Bell state here. And then they should make some local measurements, right? But these measurements, they must be chosen according to some inputs. And so here the idea, since each device here receives no input, we will make the input appear via these extra sources here, right? So these sources generate the measurement settings, X and Y, right? And based on these inputs, the parties will make the relevant measurements, as in a standard CHSH test. Of course, what is very important in a standard Bell test is that you have access to these inputs. They are part of the observed statistics. While here, of course, if they are generated by these sources, they are not observable, right? So you make them appear by having Alice output X and Bob output Y. And then there is the third party, Charlie, whom you can think of as a sort of referee who outputs those inputs X and Y. And so now Alice and Bob make their Bell test. They get some measurement outcomes. Let me denote them alpha and beta. All right, and of course, these must be also broadcasted, right? They must be announced. And so then the point is that if the conditional distribution of alpha beta given xy, right? So this would correspond to our usual CHSH Bell test. If this is non-local, then it must be that the total distribution on the triangle is not trilocal, right? And that has to be because if it would be trilocal, then you would have a local model for explaining CHSH violation, which of course does not exist. So that's a really beautiful idea. But of course, when you think about our discussion earlier on why network non-locality should be so interesting and what novel things it should allow for, well, there is a key ingredient that is missing in the construction of Fritz, right? And these are the entangled measurements. In fact, in Fritz, you can really view the instance of non-locality as a clever embedding of a standard Bell test in the network, right? So here is another distribution, which turns out to be non-local. It was discovered by in a paper published a couple of years. So Marc-Olivier, our chairman, is the R here, the first author. G is Gisin, and there are 4 Bs. And that's why we have this weird acronym now for it. All right, so what is the idea? Well, here you see the construction is already very different from that of Fritz, namely that all sources produce some entangled state. And now, in fact, it will also be the case that each party makes a same measurement. So this will be a 2-qubit measurement. This is a projective measurement with the 4 eigenstates written here, right? So you see it's interesting, it has 2 eigenstates that are product, and then 2 other eigenstates that are entangled with some variable degree of entanglement characterized by this parameter u here. Now what you can prove is the following, is that the output distribution that you get from this quantum experiment here is not trilocal whenever the u parameter here for the degree of entanglement of the eigenstate satisfies the following relation. Okay, so obviously if u is equal to 1, these 2 eigenstates here are product, and therefore the experiment is clearly not interesting. It admits a trilocal model. it's more surprising, but at this value here, which, okay, admits an analytical formula, it's too complicated to show here. At that particular value, it turns out the distribution also admits a local model. But in the middle, you can prove that this is non-local. And also, just to give you an idea of how far we are from having a good understanding of these ideas, this is a result here that holds for the exact distribution I've described here, right? So this is one where you have pure states and projective measurements. As soon as you move away from this, maybe with the exception of 10 to the minus 20 noise coefficient, but if you really want to move away from this, then we no longer know if the distribution is local or not. Okay. All right. So now my point is yet still to talk about this ideal distribution and now to compare it to that of Fritz. Okay. So intuitively we see that they are quite different. And so what are these differences? Well, first of all, the RGB4 is highly symmetrical, while the Fritz is not, right? It has clearly a V link and C as a referee. Well, in RGB4, all sources are quantum, producing a maximally entangled state. This is not the case here for the Fritz, where, of course, we have only one entangled state. The two others are just there to distribute classical inputs. And then the measurements, right? In RGB4, they are all entangled, while in the Fritz case, they are separable. All right, so this suggests intuitively that there is really something very different here between these two forms of non-locality. But of course, it's good to go beyond just intuition and some vague idea and try to formalize it. So here is a first attempt at doing so. So how could we define the notion of non-locality that is genuine to the network structure? So here is the approach that we propose. And so you can view it in two ways. So first, let me start with this one here, which is that you want to view quantum non-locality as a resource. Okay, so you take a sort of resource theory perspective. So what do I have in standard non-locality? Well, I have something like this. I have a source producing some entangled state, and then I have Alice making some incompatible measurements and Bob as well, right? And so when I put these ingredients together, I get a non-local distribution, which I will view here as a single object that I call a quantum box. Okay, so it's this thing described here in blue, right? So of course, this box is made via some ingredients, but non-locality is the resource that arises from their combination, right? So for me, non-locality is that box, right? And of course, I can produce many different versions of this box, right? I can pick any entangled state psi and choose my measurement settings. And it can be very complicated boxes with, a lot of measurement settings, a lot of measurement outcomes. These might perhaps even be continuous, and so on, right? So it's a very powerful resource. And now I look at a network and I would like to use my resource, the quantum boxes, in the network. So here is a way I can do it. Well, I will just imagine that each source can now distribute this resource. So you see it can distribute entanglement, but the point is that at the end there is a terminal attached. And in this terminal, the party can give an input and get an output. And now, of course, you see that here I have nodes that share several, or that have access to several terminals. And so in order to produce an outcome, they should combine these terminals, and this will done here via so-called wirings. Okay, so the idea is this party can input something in the, this party can input something here in the first box, gets an outcome that is then feed into the second box, and so on, right? All right, so here is a sketch of the idea, right? And so let me use here another network, not the triangle network, but the so-called bilocality network that comes from entanglement swapping. And so here is the idea of a quantum distribution that is, I would say, not genuine, right? So what is happening? Well, each party has a box here, right? And in this box, there are several terminals that are accessible. And so upon receiving some input X here, well, Alice will wire these terminals and get an output. You see that when you have a party like Bob here, who shares systems from more than one source, things can become pretty complicated, right? Because you can imagine wirings that have a very complex structure. In particular, your wirings can be dynamical, right? So based on the output here, I may decide which terminal input to next, and so on. All right, so, well, if you get the idea so far, then you have understood everything. So we want to define a genuine network non-locality via its opposite, right? So we say that some quantum correlations, PABC given XYZ here, right, in such a network, we call them quantum wireable if they admit a decomposition like this, right? So admittedly, it's difficult to test for such a decomposition because there are many different possibilities, but we will see in a minute that it's still possible to say something. Okay, and you can also make it formal, of course, given the complex structure of wirings. This is pretty horrendous. You see here an attempt at defining these things. While I couldn't resist to mention to you the comment of a referee who said the following thing, that this definition totally disqualifies as publishable work to be read by humans. The description of 5 does not seem to be fully complete for artificial intelligence automata. So I found it very fun. My colleagues not so much, but okay, I like it a lot. I kind of agree, although I think, you know, in this case, it's a good example where you should not read a formula, but just understand the idea, right? Because I think the idea of railings is very clear. All right, and so here is our main point. If you can prove that some distribution is not quantum wireable, then we are going to say it's genuine network non-local, right? That's the idea. And maybe let me just mention it here directly. So far I focused on the situation where these boxes here, these blue boxes are quantum, okay? Because, okay, we wanted to start with working within quantum mechanics and so on. You could equally just think of them as being non-signaling boxes, right? If you wanted a model independent version of this notion, that would also be possible. But here we will just focus on the quantum case. All right, so here is, as I said, an alternative view to this definition. You can think of it quite differently. So remember my point that in networks, what is really interesting is that when you combine the entanglement of states and that of measurements, and so you can also think of this notion of genuine network non-locality as testing for interesting joint measurements, or if you want, non-classical joint measurements. So why is it? Well, because wirings are classical joint measurements. These are also measurements that you can do in theory, right? So that's so interesting from this more model-independent perspective. And so what you get out of it is that if you can prove that some distribution is genuine network non-local, well, then it must use some non-classical measurement. And so what I'll do next is give you some examples of this. So here is example 0. It's too easy, but it's still an example. This is the effect of event-ready non-locality. So this is really based on entanglement swapping, right? It's the idea that you want to make a bell test between Alice and Charlie, and you go via a common relay station that is Bob, who makes perhaps some bell state measurement, and then heralds entanglement to Alice and Bob. So this is some configuration that is used in some loophole-free bell tests, for instance. And And this is an example of genuine network non-locality. It's very easy to see. If Bob was ever to do wirings, right, there is no way he can prepare entanglement between Alice and Charlie, right? A wiring will imply making some local measurement here and some local measurement there. And even if there is some feedback or some complicated structure, Alice and Charlie will still hold a separable state. And then they can never violate the Bell inequality with this. Hence, if you see event-ready non-locality, so heralded non-locality between Alice and Charlie, then you know there must be some interesting measurement that is done at Bob. So that's okay, but okay, it's still not very satisfactory in the following sense, I think, is that this non-locality here, you could also see by using the standard approach to non-locality. In fact, this is what people did already. So you can just look at the full distribution and check its non-local properties. So it doesn't really connect to the network structure. So here is another example, which is much more interesting, I think. So we have again our bilocality network. You see, we do essentially everything as before. Bob does a Bell state measurement here. Here we still have Bell states. Now what is a bit different are the measurements of Alice and Charlie. And you see these measurements are now the same between Alice and Charlie. And so if you know CHSH very well, you will immediately see that if you make aligned measurements between Alice and Charlie, the correlations you get are local, right? So you cannot violate CHSH. And you can really prove that here, the total distribution, so PABC given XZ is local in the usual sense of Bell. So if you just look at it like this, there is nothing fun happening. But if you impose the network structure, so if you impose the independence condition between these two sources, then this distribution becomes a self-test. So what does it mean? It means that within quantum mechanics, there is essentially only one realization of this data here, right? So if you observe PABC given XZ that is obtained from this construction, it implies that your underlying states and measurements are essentially these ones, right? There is no other possibility in quantum mechanics. And this is what we need, right? Because if this is the only possibility in quantum mechanics, then it means that Bob must do a Bell state measurement, right? So he must do a non-classical joint measurement. Let me also show you another example, which is connected to the question of whether we even need entanglement in the measurements, right? Because what we need is a measurement that is non-classical. It's not a wiring, but that in fact doesn't imply that the measurement is entangled. So here is a fun effect known as quantum non-locality without entanglement, something discovered by Bennett and co-authors many years ago. And so this is a form of non-locality that's very different from Bell, but has the following idea in it. So you can imagine having a set of separable states that are represented here. So you see, we consider a system of 2 Q-tricks, right? 3 by 3. And so what these blobs here represent, right, are in fact, so each blob represents a pair of states. So this pair of states here, you should think of as 0 tensor 0 plus minus 1 here, right? And here it's the same idea. This should be 0 plus minus 1 tensor 2. Same here. This is just a product state 1, 1. So you get 9 states that actually form a orthonormal basis, right, of C9. And these 9 states have the following properties: that even though all states are separable, in fact, all states are product, they cannot be perfectly distinguished by an LOCC measurement, right? And if they cannot be distinguished via an LOCC measurement, can also not be done via wirings, right? And so now you can play the game again of entanglement swapping, but you replace the Bell state measurement with this domino measurement of Bennett et al. And well, now you see we work with qubits, so you should also have qubit entangled states here, and you should do some local measurements. And this is also, in fact, an example of a genuine network non-locality. And you see, it's interesting because you really don't need an entangled measurement. This quantum non-locality without entanglement is enough. And so how does it work? Well, so the idea is we heavily rely here on ideas of self-testing. So self-testing will first allow you to characterize these states here, right? The maximally entangled state between B and C. Same thing here. Then you can self-test the local measurements of Alice and Charlie. And in the end, once you know the local measurements acting on a maximally entangled state, you also know which states are prepared here. And like this, you can self-test this domino measurement. And again, because this is a self-test, it means this is the only realization of this distribution that is compatible with quantum mechanics, right? So if you observe that distribution, well, then you must have a measurement that is non-classical. All right, so now let me come back to our initial question, which was to distinguish Fritz versus the RGB4 distribution. Of course, you can immediately see from the definition, the Fritz example is wireable, right? So it's definitely not an example of genuine non-locality. And here you can see the wiring, okay? Now, what about the RGB4? Well, had I given this talk 2 weeks ago, or let's say 3 weeks ago, my answer would have been, we don't know, but it's a conjecture. But, okay, thanks to recent progress, mostly by Pavel Sekatsky here, now we know that it's genuine network non-local. And in fact, how we prove it? Well, we prove it via some form of self-testing. So it's not a full self-testing, but a partial self-testing. But it is great because this is enough to really prove that, so again, within quantum mechanics, if you observe the RGB4 distribution, then all the measurements here must be entangled. And in fact, you can also prove that all states must be entangled. Okay, so this is a paper that will appear hopefully soon on the archive, but okay, I have to say I'm very happy about this progress, and the ideas and what Pavel did is really very impressive. All right, so I think I'm coming to an end already. Well, I discussed quantum non-locality in networks, focusing mostly on the triangle network. At first sight, it may appear that it's quite an easy problem and so on, but it's much, much harder than it seems. And it's interesting because even the simplest setting of this triangle network, even if you just imagine having binary outputs, there we still don't know exactly what is possible and what's going on. So, well, there exist some methods that allow to characterize these correlations, but in practice, it's very difficult to make use of them and to make progress. So if you have ideas, of course, causality in general is a topic that is also very much connected to quantum networks. And so if there are ideas out there that could help for quantum networks, in particular for the triangle, that would be great. Okay, and then so the focus of this talk was to convince you that the network structure is interesting, to look at quantum non-locality as it allows for new forms of correlations. Of course, the first very significant realization is that you can have non-locality without inputs. That's really something quite striking, I think. And then in this talk, I hope I could convince you that you can go even one step further and really define a notion of non-locality that is proper to the network structure. So I discussed a couple of examples, mostly focusing on the entanglement swapping network or bilocality network. But as I just mentioned, now we know this is also possible for the triangle network. Okay, so another approach in order to characterize these interesting forms of quantum correlations in network is that of full network non-locality by Armin Tavakoli, Alex Posas, and Nicolas Brunner. So here the focus is not so much on the measurements, but actually it's on the sources. And so the idea is that you want to be able to prove that all sources in the network produce some non-local correlations. So in that sense, this is an approach that is very complementary to ours. And of course, there might be other approaches. Would be great to see other ideas and other approaches to this quite interesting problem. All right, and since I mentioned it in the beginning, let me also say a few things about finding minimal examples of quantum non-locality. Finding a minimal example is always useful. If you think of Bell non-locality, CHSH is the minimal example. It's, of course, extremely well-known and useful. So is there an analog in the triangle network, for example? So can we have a minimal example of quantum non-locality without inputs? All examples I discussed in this talk have output cardinality 4. And so here we could report some progress where you can actually compress a bit this output cardinality. And our minimal example is 3, 3, and 2. Okay, so whether it's possible to have anything with less outputs is quite interesting. I think we have really looked a lot for an instance of non-locality with binary outputs, but so far we couldn't find anything. All right, so I'm at the end of the talk. Thank you for your attention and looking forward to questions.
Okay, thanks a lot, Nicolas. So we have time for questions. So are there any questions? And maybe the next...
Thank you for the very nice talk. I was wondering if, in the same way we find out the non-locality, Bell non-locality of quantum states, given two networks, is it possible to say if one network is more non-local, genuinely non-local than the other? Or in more particular, is there any connection between this framework and genuine multipartite entangled states?
Aha, okay, so that's an interesting question. Okay, so if I understand correctly, the question is whether you would be able to quantify this effect of genuine network non-locality in order to be able to compare one network to another. Yeah, well, it's certainly an interesting perspective, but so far we don't have any results in that direction, I think. And so coming back to the second part of the question, which is whether network non-locality is connected to genuine multipartite non-locality as defined in the usual sense, or perhaps it was genuine multipartite entanglement. So yes, there, I think there are some results by the group of Carlos Palazuelos. Yeah, I'm sorry, I wouldn't be able to tell you in a nutshell what is their result exactly, but if you write me either in the chat or in this alternative platform, I can pinpoint the paper, and then you can take a look.
Thank you.
Hi.
I'm sorry, I couldn't hear the end of the question. Could you repeat? Aha, yes. Yeah, so why do we work with this assumption of independence of the sources?
Mm-hmm.
Yes, well, of course that's a very good point, right? So I would say depends on what sort of problems you have in mind. So for example, if you look at more practically oriented questions, what correlations you can imagine on future networks deployed across cities and countries. Okay, there I think the independence assumption is probably not very natural, right? Because in order to distribute this entanglement, you will need to synchronize the labs and so on. And so you will definitely have classically correlated sources. One thing, however, you can do there is that instead of looking at problems in non-locality, you could go to problems connected to entanglement. So just look at density matrices and ask what sets of density matrices you can achieve by having by having separated quantum sources that are only classically correlated. So that's more relevant, I think, towards these kind of questions. Now here, why I think it's still interesting to work with the independence assumption is more from a fundamental point of view, probably, right? Because ultimately, you can imagine that these experiments can be done in this way, right? So, of course, if you don't believe that it's impossible to have independent events, it even doesn't make much sense to talk about non-locality because you anyway need to freely choose your inputs, right? So, but if you are in that mindset, well, I think having independent sources and allowing you to look for new forms of quantum correlation is a fair point to look at.
Cool, thank you.
Maybe one more thing I can mention related to that question is that you can actually also consider models where the three sources in the triangle network become correlated by a central one. And well, of course, if that correlation is somehow not limited, right? Well, okay, then you can just have any output distribution, that's clear. But if you limit the amount of correlation between the central sources and the three other sources, you can actually still prove non-locality. In fact, quantum non-locality. So despite the sources being highly correlated.
We have one more. Do we have time?
Is it working? Yeah. Hi, Nicolas. Thanks for the talk. I just have a quick question about this definition that the referee, for example, is unhappy with, and whether there could be a way around this. Have you thought about what happens if instead of looking at wirings, which are not so easy to characterize, you look at, say, separable measurements instead? Can you get the same kind of things? Because there, I think the definition is a bit easier.
Yes. Mm-hmm, mm-hmm. Well, okay. The answer is no. We haven't really looked at it. Well, okay. Of course, you could look at separable measurements. In a sense, my feeling would be that when you do that, then then you will have to put on the side effects like quantum non-locality without entanglement. So it's definitely a possibility. Probably it would simplify, at least mathematically, the definition. Conceptually, I don't know if it simplifies it. I think you see what the referee report I mentioned, I think he was mostly unhappy with the equation, but I think with the idea it was okay. But okay, I agree with you that it's an interesting alternative. Maybe one issue I see is that it would be less easy to make it model independent, because you can have separable quantum measurements that maybe are not universal to non-signaling theories.
Okay, thank you.
So I have one last question.
Thanks for a very nice talk. Unfortunately, after your talk, but first I have a question. You considered these wirings, which are very natural for non-signaling boxes also. Have you generalized your results to such cases when you actually define some genuine non-signaling correlations or something like this?
Okay, yeah, thanks for the nice question. Well, okay, so we have, in our paper, we have actually also proposed, I think in the end, this alternative definition where you indeed allow for non-signaling boxes that are wired together. Now, if I would go again through my list of examples of quantum non-locality against such a more general model, then it's unfortunately only example 0 that I can now tell you survives. So event-ready non-locality will also be an example that is genuine network non-local against these more general non-signaling wireable models. But it's still the same idea, right? If you wire PR boxes, you will never be able to create non-locality. Now, whether the other examples would also still be genuine in this more general framework is interesting. I don't know. It's open.
Okay, thanks a lot, Nicolas. So there is one last question in the chat, but we don't have time. We have to move to the next speaker, but maybe you can answer directly.
I can answer it in the chat, yes.
Okay, so can you stop sharing your screen?
Of course. Thank you. Bye-bye.